Excellent. Thank you.
Yep.
All right, folks, we'll just be starting in another, I think, 2 minutes. And while you're waiting for this all to start, you can take the time to join the Slack. That's a good place to have some sort of back row commentary on the ongoing talks and further discussion during the breaks. All right, well, thank you all for joining us for this online FPTalks. I, as the organizer of this workshop, want to begin by saying welcome. Thank you all for coming. It's really exciting to be holding a workshop on the state of the art in numerical representations and floating point error. We've got some very exciting speakers coming up. We've got 16 talks throughout the day today. And as organizer, I'm not only excited about the speakers, I'm also excited about the fact that we have over 70 participants from over 35 affiliations scattered all across the world. And really looking forward to what happens when we put this all together. The FPTalks formula at a high level is something like this. So if we take cutting edge research in numerical representations and floating point error, and then we combine that with some short workshop style talks, I think that what we ought to get is an open academic dialogue that makes our research and our field more accessible to practitioners, to implementers, to amateurs, to those outside the formal academic space. And because this is the first time that we're holding FPTalks, my hope is that not only is this formula whole, but it also holds regardless of small rounding errors. So FPTalks is organized under the FP Bench umbrella, and I'll be telling you a little bit more about the FP Bench project in just a little bit. But it is also being sponsored by the Applications Driving Architectures Center, that's JUMP Center, organized by DARPA and the Silicon Research Corporation. And thanks to their sponsorship, all of the speakers will be getting a snazzy FP Bench t-shirt in the mail. So look out for that, and thank you to the ADA. But let me first tell you a little bit more about FP Bench. FP Bench is a project that we started organizing, I think somewhere around 2016. And the idea of FP Bench was to strengthen our community by building community resources and doing some community building for this academic research into numerical representations and floating point error. So I'd like to tell you just a little bit about the projects that we've been doing under this goal. And I'll start with some community resources that we've been working on. Maybe the most obvious community resource that's in the name are the benchmarks. So we've collected something like 130 benchmarks from different published research papers and also unpublished work by researchers in this area. We've collected them and added metadata describing example inputs, error tolerances on those benchmarks, what sorts of, where those benchmarks might be used, and citations where those benchmarks have been benchmarked against. Now, those benchmarks on their own, a benchmark is a benchmark, but to make them more usable, we've also built a set of compilers. And those compilers can transform this benchmark code into languages from Mathematica all the way to JavaScript so that you can use them as input to any research tools you're building. And not only do those compilers do a direct translation, there's also a set of transformations that we've implemented for this benchmark language that we've developed. So we can automatically do things like loop unrolling, common sub-expression elimination, or function inlining with the pre-built tool. So this is something that basically you can use to modify the benchmarks to suit your use case. Maybe your tool doesn't support loops, or maybe it needs preconditions in a certain format, and automatically transform them into that to make it that much easier to get started using these benchmarks. And finally, these benchmarks, they're in a standardized format that we've developed. We call it FPCore. And not only is this an easy to parse and unambiguous syntax, we've also built some careful semantics around tricky things like library function calls, mixed precision code. And as you'll hear from Bill after lunch, our most recent release of the standards, FPBench 2.0, also includes support for tensor computations. So these are resources that you can go ahead in your research, in your work, and use them right now. You can contribute benchmarks or download the benchmarks that we have already. You can use the compilers to transform them, modify them for your tool, and you can support this FPCore format as a standard input format for any tools that you develop. So let me actually take a quick break from this presentation and just show you directly what those tools and resources are like. This is the event webpage, and at the top you can directly see links to the benchmarks, compilers, and standards. So let's start with the benchmarks. And here on this benchmarks page, you'll see a list of all of the benchmarks that we have. You can click on any one of them and see additional information they may have. So you'll see here that these benchmarks not only come with pretty extensive preconditions, as well as the program itself, which in this case is pretty simple because the precondition that makes the benchmark complex. You see that they're also annotated with precisions, and in some cases also citations for further examples. Like, for example, here you can see citations to papers and books that these benchmarks are sourced from. You'll also see that at the bottom, we've linked to a few external tools. If you're developing a floating point or numeric representation tool that can take FPCore inputs and is accessible over the web, please let me know, because we'd love to make this, we'd love to add a link to your tool right here, make it even easier for people to discover your work. So we've got this whole list of benchmarks here, but not only that, this list is also searchable. So I can search for a specific benchmark by name, like this. I can search it also by which operators it is using. Like, for example, if my tool has just implemented support for the exponential operator, I can search specifically for the 16 benchmarks that have it and download all of them. And you can even search directly for tools, for benchmarks cited in or used in a particular paper. And you can just download basically a little kit to reproduce the results of that paper. And I'm sure this benchmark suite could grow and become even better. So we're open for contributions, and please, if you have benchmarks you use to evaluate your tools, whether they're in this FPCore format or any other format, please click this link, contribute to our benchmarks over GitHub. I also mentioned that there are compilers and standards. The compilers, you can find instructions for installing them on the website, and you can see that it basically provides a way to export our benchmark format to any other language, and there's quite a long list, as well as transformations that you can do, like common sub-expression elimination. Finally, you can browse the standards right here. And this includes the standards that we've just released, handling tensor computations and function calls. So you can browse those right here. You'll see the benchmark format, the syntax, detailed description of the constants and functions supported, as well as a description of the semantics. So you can browse that at your own leisure, but please do and use these in your own work. I think you'll find it can be quite helpful. But besides the resources that we've developed, the benchmarks, the compilers, and the standards, we've also recently been pushing to do some more community building as well. The first place we started is gathering a list of papers using the FPBench benchmarks, making it easy to compare your work to other work that's using the same benchmark and find papers that might be good baselines to compare your work against. But we've also expanded that into a list more or less comprehensive of all of the floating point research tools and numerical representation tools out there. These are loosely organized. They're maintained by Mike Lamb, and you can find those on our website as well. And then finally, maybe the most recent example of community building we're doing is this very workshop, which we're hosting for the first time. As I've said in the emails that you've received, all of these talks will be recorded. They'll end up on YouTube, and hopefully they'll make our field more accessible to others. So these are also places where you can contribute. You can add yourself as a user of the FPBench benchmarks, explore the list of floating point and numerical representation tools we've collected. And of course, all of you are already attending this workshop, so you've already gotten started. So that's FPBench, which is the sort of community resources and community building project we've been doing. And if you'd like to find out more about that, go to fpbench.org. And now I want to tell you, just to wrap up, a little bit about the logistics of how FPTalks 2020 will work. You're already all on Zoom, so you know that that's how we're doing it. The schedule is going to have 4 sessions, each an hour long, covering really exciting talks from sort of all over the spectrum of floating point and numerical representations. You'll note that the talks are spread pretty widely through the day with generous breaks. Partly that's to make it possible to attend FPTalks and to give talks despite the global pandemic from across the world. But that doesn't mean that FPTalks stops happening during these breaks. So I'd like to invite you to continue discussions and any sort of further questions you have for the speakers on 2 tools that we've set up, Slack and Gather. If you're not familiar with them, Slack is this group chat application, and we've set up not just a general channel for FPTalks, but also some specific channels if you'd like to learn more about the benchmarks, the compilers, or the standards. So that's a great place to discuss anything that you want to know about FPBench. But of course, you can also use it to discuss any talks that you see, ask further questions of the speakers, and so on. The other tool that we've set up is something called Gather. Gather is this kind of like informal social chat application using video chat. You sort of have an avatar where you can walk around the world, and when you're close to people, you can see their video feeds and talk to them. I used it for the first time about a week ago for the PLDI conference, and I think it's pretty exciting. So hopefully you'll check it out and see if it works for you. And you can find links to both Slack and Gather on the main event website. You've also received them in your email. So just a bit about the logistics. This is a Zoom meeting, so please keep your microphones muted. However, we will be taking questions live. If you open the participants panel, there should be a button at the bottom of your screen labeled participants. You should see a button that says raise hand toward the bottom of it. And you can click that, and that will tell me as the moderator of the session that you'd like to ask a question, and I'll call on you and the speakers will answer questions. So that's how we'll do live questions for the speakers. Finally, I should note that all of the talks are being recorded and also live streamed to YouTube. What that means is all of these talks will be accessible afterward, and hopefully we'll make high quality recordings of them available on the website shortly after FPTalks is over. If you've got any questions that you want to ask about FPTalks, if you have technical difficulties, you can contact me. Probably best is contacting me on Slack. I've got a second screen on my right here, and I'll be on Slack the whole time. So if you have any questions or technical difficulties, you can ping me directly. with a direct message on Slack, or you can join the support channel if you think your questions are sort of more generalizable that someone might be able to help you out. So with that, I think those are the basic logistics out of the way. I don't want to take up too much time. I want to jump right into some of the really exciting talks that we've got going. So in summary, welcome again, everyone, to FPTalks 2020. I hope you are as excited as I am for the next day of talks. And with that, I'll open the floor up to questions, and we can get prepared for the next talk. So if there are any questions, I'll take them now. If you want to ask a question, just click participants at the bottom of your screen. It should be to the left of share screen. And then on the sidebar that opens up, you'll see a button labeled raise hand. That's how we'll do the queue for questions. Meanwhile, Thierry, are you ready to go?
Yes, Pavel, I'm ready. Yeah.
Awesome.
So, I will go ahead and share.
Yeah, if you could start the recording on your end and also start the screen share.
All right, so I think I'm recording now, right?
Great.
Okay, thanks, Pavel. Hi, everybody. My name is Thierry Tambe. I am a PhD student at Harvard University. I'm pleased to be invited to FPTalks to give this talk. It's called AdaptivFloat, and it's a data type for resilient deep learning inference. So let's get started. So in order to obtain higher GNN compute density and energy efficiency, we have seen that a plethora of reduced precision quantization techniques have been proposed. And what we see is that in this line of research, a majority of the proposed quantization techniques are fixed point or integer based. Furthermore, typically these fixed point techniques are frequently evaluated on convolution neural networks such as ResNet. However, emerging models such as in natural language processing actually exhibit a much wider parameter distribution that cannot be faithfully represented by these common fixed point or integer data types. And that's mainly due to the inherent lack of dynamic range. So in thinking about a data type for deep learning, it is clear that we need a solution that can adapt to the large parameter variability seen in deep neural networks parameters. So in this work, we address this shortcoming by proposing a floating point-based encoding blueprint that we call AdaptivFloat. Notably, AdaptivFloat is able to adapt to the statistical distribution of the GNN parameters. It is found to produce noticeably higher inference accuracies compared to other prominent data types, as I will show. And it is resilient to aggressive bandwidth compression. And finally, in this work, I know this is workshop is much more algorithm based, but we were actually able to come up with a hardware prototype which leveraged the AdaptivFloat algorithm to actually produce lower energy overhead. So let's start first with the algorithm, and I will show how it adapts to the parameter distribution of the deep learning model. So AdaptivFloat is floating point based, so which means that it already produces a higher dynamic range compared to an integer data type. Now, what we do is that on a layer by layer basis in the neural network, AdaptivFloat further maximizes its dynamic range by formulating an exponential bias that we call EXP bias. And this EXP bias is computed based on it's computed from the maximum absolute value in the tensor. So then based on this exponent bias, AdaptivFloat dynamically shifts the exponent range of the data points in order to encode as faithfully as possible the larger values in the tensor. So the intuition here is that in neural networks, typically the larger values tend to have a bigger impact on the accuracy of the model. So we actually, so we leverage this insight to essentially shift the exponent range of the data points to try to faithfully as possible represent these larger values. And this is actually illustrated here in this slide. And you can see here that going from some ResNet 50 layers to some transformer layers, the exponent bias varies. It goes from -10, -9, all the way down to -5. So this is how the AdaptivFloat algorithm is able to shift its exponent range to faithfully represent the data points, the parameters in the neural networks. I should also mention that the AdaptivFloat number system generally follows the standard floating point specification. However, we break from standard IEEE 754 compliance by not encoding G-normals. So by doing so, we significantly simplify the hardware design, as we will show later. And it turns out that G-normals values are small enough not to affect the inference accuracy. So in deep learning, it turns out that we don't really lose anything by not encoding floating point G-normals. Now, the main problem arising as a result of not using G-normals is the lack of representation for the 0 point. And that's because, as you know, 0 is a floating point G-normal number. So in AdaptivFloat, what we do to solve this constraint is to sacrifice the positive and negative minimum values to allocate a slot for the 0, as shown in this figure. We also note that the AdaptivFloat algorithm is self-supervised in the sense that the algorithm only relies on the unlabeled data distribution in the network. So it can be easily plugged into any machine learning framework at either learning or inference time. And the user just needs to provide the input tensor, the required bit precision, and the exponent bit width. So now I would like to show some result which will describe the resiliency of the AdaptivFloat algorithm during bit compression. In our experimental setup, we consider 3 well-known neural networks, the transformer, an attention-based sequence-to-sequence network, and ResNet 50. Across a diverse set of applications here. And then we also note that these 3 networks exhibit relatively narrow to wide parameter distribution as shown on this table. Furthermore, for each of these networks, we evaluate and compare AdaptivFloat against other prominent data type commonly used in deep learning, namely uniform integer, posit, block floating point, and IEEE-like float. Notably in posit and in IEEE-like float, their dynamic range is fixed, which means that it does not adapt to the data distribution of the layer. So we began by quantifying the quantization error of these data type with respect to the baseline FP32, 14.32 single precision. So if we were to look at the root mean square of the quantization error computed across all the layers of the transformer model, let's say at 4-bit precision, we see here that AdaptivFloat produce the lowest average quantization error compared to all of these other data types. Furthermore, we also see that among the self-adaptive data types, which is AdaptivFloat, uniform, and block floating point, AdaptivFloat exhibits the lowest error spread, as shown here. And and this observation is maintained if we were to look across, models, transformers, sequence-to-sequence ResNet, and also across various bit precision, 4-bit, 6-bit, and 8-bit. AdaptivFloat is able to produce overall the lowest quantization error. Now, if you were to look at the accuracy trend for post-training quantization, we generally see a trend that as the weight bit precision decreases from 16-bit down to 4-bit, AdaptivFloat, which is shown here in the red star, is consistently produces the higher performance. Whether we look at the transformer BLU score or the sequence-to-sequence order rate or ResNet top 1 accuracy. So overall, AdaptivFloat is able to demonstrate much greater resiliency towards lower word sizes. Now let us look at how AdaptivFloat quickly is implemented in hardware. And this is it's algorithm centric, but I would just quickly want to show what we do in the hardware. So first of all, we note that the plurality of commercial ML accelerators, they implement monolithic integer arithmetic, such as in NVDLA. And here the computational data path of such integer-based accelerators is need to have a scaling factor to scale the partial sum after Mach operation. So what we do here and what we propose here is a hybrid float integer processing element, which provides a cost-effective compromise between the high accuracy of the floating point computation and the greater hardware density of fixed points. So essentially we do floating point to perform the matrix vector multiplication. And after the matrix vector multiplication, we switch to fixed point for the post processing. And I mentioned, so in the post processing, the exponential bias which are obtained from the AdaptivFloat algorithms, they are stored in the single register, and this is used essentially to shift the partial sum after the Mach operation. So what we see overall is that, and so here the HFINT is the accelerator that we propose using AdaptivFloat. What we see is that it is able to produce lower per operation energy compared to an integer-based processing element. However, we do end up with a higher area compared to an integer-based PE, and that is because a floating point Mach essentially is made of multipliers, shifters, and adders, and it is not as compact as a fixed point Mach, which is only made of multipliers. So to summarize here, so we made the observation that emerging neural networks, such as in NLP, exhibit much wider parameter distribution that cannot be faithfully represented by common fixed point or integer data types. So we address this shortcoming by proposing a floating point-based encoding blueprint called AdaptivFloat for neural networks. And notably, AdaptivFloat adapts to the GNN parameters by shifting its exponent range on a per layer basis. And AdaptivFloat is found to be resilient to aggressive bit compression, and it also yields higher energy efficiencies in hardware compared to fixed point solutions. So altogether, the adaptive floating point algorithm hardware co-design offers a tangible accuracy and energy advantage over fixed point solution. Thank you very much, and I'll be happy to take some questions.
Okay, thank you very much, Thierry. I think we have a question from Ganesh.
Yeah. Yep.
Hi, I hope the background noise doesn't bother you. Nice talk, Thierry. Yeah. I'd like to know how you store store the weights in memory and how you transfer it to the chip or the accelerator. Sometimes the format of storage in memory could be different from what the computational units use. So do you do conversions or use intrinsics in the transmission?
Yeah,
or is it all uniform?
Yeah, so what we do here is that before we store the weights in the buffers of the accelerator, we would already quantize those weights in the AdaptivFloat format, right? We do this in the machine learning framework. In our case, we use PyTorch. So we would essentially, still within the PyTorch environment, we would essentially we plugged in the AdaptivFloat algorithm in PyTorch to quantize those weights in AdaptivFloat, and then we would then fetch those weights from PyTorch and store them in the buffers of the accelerator. And so from PyTorch, we store the weights in the AdaptivFloat format, but we also, most importantly, we also store we also get the exponential bias from AdaptivFloat, because this will be useful eventually to shift the partial sum when we go from floating point to fixed point.
Thank you. Yeah.
If anyone else has questions, please use the raise hand button in the participants window. We might have time for one more. Actually, if you don't mind, I have a question.
Yes.
The exponent bias,
Mm-hmm.
is that inherent in the way that you lay out the chip? In other words, is the chip fixed to a specific exponent bias?
Oh, no. So exponential, no. So the exponent bias value is a parameter that is stored in a register on a chip, right? So you can update this value, as you need, and so essentially you will have as many exponent bias as the number of layers that you have in the neural network. So if your neural network, let's say, has 12 layers, so you will be able to store 12 different exponent bias inside the registers of the accelerator on chip. All right. So now when we do inference on this neural network, we essentially are able to get this exponent bias when we compute that layer, the required layer. Does that make sense, Pavel?
Yes, thank you. Okay, I think we should move on to the next talk. So Thierry, if you could exit the screen share.
All right, and I will.
And our next talk will be by Eva Darulova. So maybe do you want to start recording and then screen sharing?
Yep. So I just hit the record button.
Okay,
that's correct?
Good. Yes, that's right.
Okay. And now, you hopefully see my screen.
That's right. Go ahead.
Okay, thanks. Wait, this is running by itself. Okay, hopefully now it's not going to anymore. All right, thanks, Pavel, for the introduction. So I'm Eva. I'm tenure track faculty at the Max Planck Institute for Software Systems, and I want to tell you about our recent project that I did in collaboration with Anastasia and Helmut at TU München. So we're interested in synthesizing floating point, so loop invariants for floating point loops. And this is again not working. Wait, why can't I move? Okay. I will have to restart this. Okay, now. So we're interested in synthesizing loop invariants for loops such as the one that you see on the screen that is simulating a dynamical system. And the trouble with these kind of loops is that they're potentially unbounded. So if you want to analyze their behavior, we cannot simply unroll them. So when we have this issue, then one standard approach to still say something meaningful is to find a loop invariant. And in particular, that's a property that holds at the loop entry and it holds after every iteration. So this way we have some property that we can still compute even if we don't know how many loop iterations we're going to execute. So verifying such loop invariance is relatively straightforward. And I'm just going to repeat what you probably already know. We do this by mathematical induction. So we first prove a base case. That means that a precondition, so whatever is true before the loop, holds at the loop entry, so that the invariant holds at the loop entry. And then we're going to assume the loop invariant, that it holds before some arbitrary ith execution, and show that it will also hold after the ith iteration. So in terms of a formula, we will assume the invariant, we will assume the loop condition, if it's more complicated than just true. We will assume that the loop body executes and then show that the invariant with the updated loop variables also holds after the iteration. So the kind of loop invariants that we're looking for are ones that bound values of variables. So the two bounds that I show here for x and y, those are actually invariant for this kind of loop. And these are useful, for instance, when we want to do safety verification, so we can show that x and y do not reach some unsafe state, but they're also a prerequisite if you want to bound round of errors. As with many other loop invariants, just these simple bounds are not enough. So if we actually want to prove that these bounds are inductive, so that they are an inductive invariant, we actually need to provide an additional constraint, for instance, in this form as a polynomial inequality. So just to show you visually how this looks like for this example, the green box, that's the precondition. So that's where we start off. The outer box shows you the actual bounds here, and the polynomial inequality that translates to this ellipsoid that bounds the light blue points that show the loop, so the actual concrete executions of the loop. So we see that just the loop bounds, they're not very tightly covering the executions. We really need this polynomial inequality. So that's really what we are after, what we want to find. In principle, we could try to use existing approaches that do exact reasoning. Unfortunately, with floating points, exact reasoning is not practical simply due to the complexity. So by exact reasoning, I mean taking floating points as bit vectors, for example. However, it turns out that exact reasoning in this case is not necessary, because there is not just a single invariant, rather there is a whole set of possible invariants, and we just need to find one of them. If we have the choice, obviously we would like to find the smallest one, because that will allow us to do more verification after the loop has finished. So our goal is to find one of these loop invariants, and if we can, one of the smallest. The approach that we take to synthesizing or finding these invariants is a relatively standard approach in inductive synthesis based on counterexamples. So CGIS works in two steps, a generate and a verify step. The generate step repeatedly will generate candidate invariants that are then passed to the verify step that tries to check whether these are actually inductive invariants. We can, for instance, do this check using an SMT solver, simply querying the solver for the two conditions I have shown you on the previous slide. Now, if the SMT solver says, yes, these conditions hold, then we have found our inductive invariant and we're done. In case it does not, because our candidate invariant was not actually inductive, for instance, the SMT solver is going to say no, and we will generate the next invariant. Now, if we just have this loop, then we're essentially just randomly trying different invariants, hoping one of them is going to be inductive. So that's not particularly effective. This really only works if the SMT solver can provide us with a counterexample that we can then use to rule out a relatively large space of other invariants. So basically, we want to use this counterexample to learn a little bit more so that the next candidate invariant that we produce is not just going to be a random guess. So one approach for generating these candidate invariants that has been successful in the past, for instance, in the Microsoft Driver Verifier, is based on a finite set of predicates that, for instance, you can guess from the source code of a program. And then you generate candidate invariants as a conjunction of a subset of these predicates. Now, for our purpose, for floating point loops and the invariants that we are looking for, this unfortunately doesn't work because what we need to generate are essentially the coefficients of the polynomial and the interval bounds. And these cannot be expressed as a finite set of predicates. So we need to find a different generation step to make this work. Now, before we do that, we first initialize our loop. And we do this by just simulating it. So we draw random inputs from the precondition set, and we just execute the loop and record the points that we see, because these are exactly the points that the invariant has to cover. Now so just to visually show you what that looks like, the green box is again our precondition. From this, we start drawing random inputs, and the blue points show you just the executions of the program. So once we have this initial set of points, we compute the convex hull, because we are essentially interested in an outer bound, so we don't need all the points that are in the middle. And then based on this convex hull, we will fit a polynomial, for example, with least squares. Now, this polynomial fit is noisy because it's based on a random subset of points that you can find in a concrete execution, but it's only a subset. And second, the least squares, or whichever other method you use, is also going to be noisy. So that's why we have these very particular numbers. To get rid of some of this noise, we will just round the coefficients, and then we will also round the bound on the polynomial outwards, such that we cover all of the points. So this is best explained again with an example. So the light blue points, that's our concrete executions. The dashed line, that's the initial polynomial fit. And the solid line, that's the candidate invariant that we finally generated. So now we have a candidate invariant, so we have to verify it. As I said before, exact reasoning does not really scale up. We have tried to use the floating point SMT theory to verify our candidate invariants, but this was not really scalable. So what we do instead, we encode the inductiveness properties with real values and bound the round of error that happens during one loop iteration by an additional error term. And we do this round of error bounding with an external tool. This turns out to scale sufficiently well. However, for our example, we'll get a counterexample. So the initial candidate is not inductive. And based on this counterexample, we could now try to generate another invariant. So again, take the convex hull, etc. Just doing this does not really work. And the reason for that is that this counterexample that the SMT solver has returned is random. So the solver can pick any point that it likes. That is a counterexample. So if we just go by this one single point, then we will essentially skew this shape that we are looking for in some random direction. So the point that I'm trying to make is that we want to generalize from this counterexample, so we explore the space a little bit more evenly. So in our algorithm, we'll add some additional points, so some additional counterexamples, for example, by using the symmetry of the ellipsoid shape, or we can ask the solver for some additional example as well. And then starting from this, we'll do another round of simulation, another round of concrete points that all have to be covered by the new candidate invariant. So if we compute the new one, then you'll see the dark blue solid shape here that now is a little bit larger and has a slightly different shape than the one that we had before. And then we basically repeat, and hopefully after a few iterations, we will find our final invariant. So in our example, this happens after 6 iterations. Now, obviously, this algorithm is incomplete, so it's not guaranteed to finish and can diverge, but we've observed that it actually works quite well on the set of benchmarks. So this is to conclude my talk. I hope I have convinced you that you can use CGIS for generating floating point loop invariants. And the key points to make this really work is to use a noisy polynomial fit. You have to abstract the errors to do the verification. And the crucial point is that you have to generalize from the counterexamples. And we have been using this using simulation. Now, this procedure works for nonlinear loops, which is more than state-of-the-art approaches can do. And it's also computing tighter invariants, at least in our evaluation, than state-of-the-art tools. And that's all I had to say.
Okay, thank you, Eva. Really great talk. If you want to exit the screen share, and I think we have time for questions. So Zvonimir had his hand up first.
Hi, Eva. Thanks for a great talk, and it's nice to see you remotely, at least. Too bad that we didn't all meet in Dutchtool several weeks ago. I was really excited about it. So I'm curious. You know, usually when you are generating loop invariants, it's driven by some kind of property you're trying to verify, and you are trying to generate an invariant that is good enough to verify the property. So in your case, I mean, do you have such properties in mind, or are you just trying to generate kind of tight invariants, let's say, compared to other approaches, maybe?
So we do not rely on this target property. And the reason for that is if you're actually interested in computing round-off errors that are happening inside the loop, you do not have this property in the first place. So our goal has really been to just compute the tightest ones.
Got it. Okay, thank you.
Okay, so it looks like we should probably move on to the next talk. And I see that there are more questions in the more hands up in the participants window. So if your question has not been answered, one good place to put it is a thread I've started on Slack where we could log additional questions, and also Eva could go around and answer them as well. And I think that's going to be a little more permanent, a little easier to refer to than the Zoom chat. Okay, so our next talk will be by Heiko. Heiko, do you want to start recording and screen share?
Yes, just a second. Should work. Okay.
It does.
Okay, so hi everyone. Thanks, Pavel, for the introduction. So I'm a PhD student at MPI SWS in the group of Eva Darulova. And today I want to talk to you about our ongoing project to build a fully verified optimizing compiler for floating point arithmetic. But let's start things simple. So compiler verification has seen a big success story in the last years, where unverified compilers like GCC or LLVM give you no guarantees on the machine code that they spit out when provided an input program. Verified compilers like the ComCert-C compiler or CakeML for the verified implementation of standard ML will give you a proof that they preserve the exact meaning of the input program that you've given them in the machine code that they spit out, which is exciting. But let's look a little closer here, especially with a focus on floating points. So unverified compilers, as I mentioned before, GCC or Clang, they will not actually preserve IEEE 754 semantics. And they give you no guarantees on the result that they produced, but in turn can aggressively optimize your floating point program. And on the side of verified compilers, ComCert had this paper in 2015 by Bordeaux et al., where they extended the ComCert verified compiler with an implementation of floating points. And this was an amazing first step because the compiler fully preserves IEEE semantics with a formal proof, guarantees you to preserve the exact same meaning, but unfortunately, it cannot apply floating point optimizations. So there is a clear need here for supporting floating point optimizations in a verified compiler. And for the rest of my talk, I want to tell you about this ongoing project by kind of zooming in to two key parts of it, which is building a semantics that supports adding these optimizations to verified compilers and finding a way to reason about the optimizations that have been performed by the compiler. And I'll start by the semantics, where I would like to briefly speak about icing, which is our new non-deterministic semantics for floating points, which we presented at CAF last year. And the key idea is that it gives you, one of the key ideas is that it gives you fine-grained control over where optimizations are applied. So this is the OPT annotation that we add here on this slide. Then it supports a subset of GCC's so-called fast math optimizations, so the ones it applies to floating point programs. And as an example on this slide, I'm showing you commutativity of multiplication at the bottom here, and FMA introduction, which replaces a multiplication and addition by the fused multiply add hardware instruction. And in our paper at CAF, we give implementations of 3 reference optimizers. The first one being an IEEE preserving translator, so kind of recovering the behavior you would have gotten from ComCert. And then a greedy optimizer that models kind of what you would get from GCC, so just greedily optimizing to its best possible, and a conditional optimizer, which tries to leverage some more knowledge you can get while optimizing. All of this is fully verified in the Hall 4 theorem provers, so we have correctness proofs for each and every step of the optimizations and for the semantics. And I want to briefly talk now about some of its key ideas for getting the optimizations to work. So the first one here is the value type that we use for icing. In IEEE 754, if you take this example expression on the left-hand side and evaluate it, you get a floating point word representing the result in 64 bits, for example. But in icing, what we do is, if we evaluate the very same expression, we produce a tree representation of the result. We call that a value tree representation. It allows us to carry information about the structure of the expression into the semantics by using a lazy data type for expressing floating point values. And how do we make use of this in the semantics? So if we take, again, just a simple example expression that we can optimize, so I added the OPT annotation here, and we use the example optimizations from before, what we're going to do is we say these optimizations are now included within a run of the semantics. So the semantics can non-deterministically optimize based on these optimizations. And with the fine-grained control, we limit where these are applicable. And there's 3 possible optimization results. So OPT1 here means that only optimization 1 has been applied. OPT2 means that only the second optimization was applied. And no OPT is kind of the IEEE 754 preserving result that you would get. And note that because we don't add commutativity of addition to the allowed semantics, allowed optimizations, sorry, it will not be possible for the semantics to produce the result on the left-hand side of the slide. Putting all of this together, this makes icing a direct fit for floating point arithmetic, giving you fine-grained control and supporting different styles of optimizations. But now to kind of step back a bit, what does this all mean for a compiler? So in icing, we've integrated the icing semantics into CakeML source semantics, which is one of the existing bigger verified compilers. And what we first prove is that from a run of deterministic CakeML source code, we can recover kind of a non-deterministic icing execution by the correctness proof for the optimizers. So basically proving that the optimizer had to pick one of the possible results of running the icing semantics. And from the CakeML compiler correctness theorem, we then get a proof that compiling this deterministic floating point code to x86 or ARM code has the exact same meaning. And now the question is this enough? Are we satisfied with this result? And I think it's missing one of the key points here, which is the roundoff errors. So let's look at an example. Let's say we have this Doppler floating point program that I'm showing you here on the slide. And suppose we again use some relatively simple example optimizations. This time I've swapped out the commutativity of multiplication for commutativity of addition and kept the FMA introduction. And let's say we can tolerate an error of 2 to the minus 10 of this program. So as a maximum round-off error of the resulting program that we want to get from the compiler. If we optimize this with our icing optimizer in CakeML, we can introduce an FMA here. And we now, or I will now show you kind of our work in progress theorem statement that we obtain for this example optimization. The first part of the theorem is if we run the optimized Doppler program, there is a word W which is printed to standard out. So this is kind of the CakeML correctness once we add IO code around it. Then we get a proof that the unoptimized Doppler kernel, so the initial program, also returns this W, which is icing's backwards correctness proof from before. And now comes the cool part. The round-off error of the optimized program is upper bounded by the user provided bound 2 to the minus 10. And we prove that using existing static analysis tools for round-off errors. Existing static analysis tool for round-off errors called Flover. And you have to take this with a grain. Yeah. And this is our kind of work in progress theorem that we can prove. To conclude, I've given you an overview of our work in progress integration of icing into the CakeML verified compiler, which is why I call it putting the icing on the cake here, because it gives us a fully verified optimizing compiler for floating points. And with that, I would like to conclude, and I'll be happy to answer any questions.
Okay, thank you, Heiko. Great talk. If there are any questions from the audience, if you could just use the raise hand button. Meanwhile, I will start by proxying a question from the Slack. Actually, Santosh, do you want to ask it directly?
Yeah, let me go ahead and ask you directly. So nice talk, nice work. So there are two questions, actually, I was typing it out. First question is, I was confused, like, what is your refinement condition for the optimizations? And the second question is, so you have a composition, like let's say you have a pipeline of floating point optimizations and you compose them in various ways. Reasoning about rounding errors, like the bound for the eventual result is much harder. Like, I don't know, like how you are able to say a pipeline of optimization satisfies the user bound.
Yeah, so I'll answer your questions one by one. So the first one was, how does the simulation proof basically work for the compiler? And yeah, I kind of glimpsed over that a bit here in the interest of time. So what we do is we prove that the result that you get from syntactic optimization, so if you run the syntactically optimized program and obtain a value, that value must have been the result of running the non-deterministic semantics with the optimizations that you used enabled. So just shifting the optimizations into the semantics basically, and giving a schedule how the semantics could have gotten there.
So effectively you're not reasoning about rounding error. Like what you're effectively saying is just like, oh, the compiler is choosing one of the optimizations in your set.
Exactly, there's no round-off error reasoning there. And we do that separately on purpose. So in our current work in progress pipeline, the round-off error reasoning is done at the very end. So you would first run all of your optimizations, get your simulation through the icing theorems, and then just establish this relation on the error by running the Flover tool or any other static analysis tool for round-off errors once on that particular kernel that you optimized.
So just sorry to follow up, like maybe we can take this offline. So I'm kind of like confused, like for example, LLVM does, like take a mainstream compiler, GCC or LLVM, they have a suite of optimizations, right? They just do these optimizations. So then they trivially satisfy the refinement condition that you have?
Yes. So in that sense, of course, they trivially satisfy this refinement condition if you were to just add them. So what I kind of glimpsed over also is that Ising has a very strict format in which you express these optimizations. So they are written in the form of these very small peephole optimizations. Just replace this small sub-expression with this small sub-expression. And bigger things like the LLVM multiplication pass, which does all the compressions on and refactorings and everything, couldn't be just straightforwardly added. So you would really have to either do this simulation proof with only these small optimizations, or of course, if you want to cheat, just increase the expressiveness of the optimizers.
Heiko, would it be okay if I just added a little bit to that?
Please go ahead, Zach.
So you know, Heiko's absolutely right, and so sometimes what you said does hold. You know, you trivially satisfy that condition, but there's really no way around it with floating point because you're going to change the control flow behavior, and so you can't get the traditional backwards refinement easily. So what's really cool about Heiko's approach is that you can think about it as a compromise somewhere between, you know, what programmers expect, right? Like for a lot of floating point code, the programmer would be happy to have FMAs introduced, reassociations, et cetera, if it led to better performance, and going to like a full real semantics, and then getting the compiler to try to do this compilation and guarantee an error bound. And we'll see Hans Bohm's talk in the afternoon about the real APIs. So this is a different point. And that's why that second ingredient Heiko was talking about, integrating the error analysis, is so crucial, because that's what gives meaning to that simulation. Because otherwise, you're right, it's not too tricky. But by having that interface where you can make that guarantee, that's how we sort of bound, you know, how bad things can get by this rewriting.
Okay, well, I see that there are still some more questions in the thread, but I also wanted to take a moment just to explain how the end of the session will go. So thank you again, Heiko, and also Eva and Thierry for really exciting talks to start us all off. Since we're at the end of the first session, we're moving into the first break, and a great place to sort of follow up on these talks. And also I've already heard some people say how excited they are to, you know, see each other again, virtually as it were. Another great place to take that is the Gather instance. So I'll be moving to Gather in just a moment, and hopefully those of you interested in sort of continuing these discussions in person, or at least over video chat, I'll see you there as well. So see you on Gather for about an hour, and then at 10 Pacific time, we will be rejoining for our second session, starting off with a talk by Hans Bohm.